But with the recent results of JWST, there was a great telescope, webtelescope.org. We can go and see some of the latest press releases and all the exciting things it's doing. Just like this one that came out a couple of months ago. This is Sagittarius B2. It is a star-forming region towards the center of our galaxy. It is amazing how many stars you can see and their dust and gas. These are all baby stars that are going to host planets, perhaps. If you want something a little closer to home, this is another press release from just a month ago. This is Uranus in our own solar system. This is a real image from JWST. And you can see the ring of Uranus as well as the satellites that orbit it, including this little guy, which might be, I think, is an undiscovered moon of Uranus. So now I'm going to show you one of my favorite press releases for an exoplanet, a rocky exoplanet. It's okay if you're not odd. It's a little less impressive, I know. You'll have to believe me for now, but maybe by the end of this talk you'll appreciate that a lot of time and effort went into gathering this data point, and a lot of theory went into producing these models that we compare that data point to. This one little data point is telling us that the rocky exoplanet, TRAPPIST-1c, probably does not have a substantial atmosphere. So why can't I show you a better picture of an exoplanet? Maybe this is disappointing. And I want to take you back to soon after JWST started returning data. Maybe I don't have to translate this for as many people here as I usually do, but this is a post from a French astronomer saying this is a photo of Proxima Centauri, the closest star to the sun. It's 4.2 light years away, taken with JWST, and look at the level of detail, how amazing. This is a joke, and this is an astronomer joke that we thought was very funny, but some people kind of took it a little too far, because this is not Proxima Centauri. This is a piece of Solon. But in this joke, there is actually oh, thank you. Oh, but that we do like that. Is that okay? Otherwise, okay, great. Yeah, this is Solon, right? In this joke, though, it was actually a really sort of powerful lesson, which is that even though JWST can see stars forming towards the center of our galaxy, in most of exoplanet science, basically all of it, we are looking at things that are very close by, but too faint for even JWST to see the difference between one side and the other. JWST cannot resolve the surface of Proxima Centauri. It can see light from it, but we can't tell the difference between light coming from this point to this point to this point. It all comes in on just one single pixel. But all is not lost. We have really great artists who do these beautiful artist impressions. These come along with every press release. So every time you see an exoplanet press release, think these are really nice salons. But there is information here, and what all of these are telling us is that we have detected so many exoplanets, over 6,000 at this point. And we've detected big ones and small ones, and hot ones and cold ones. And we've even detected molecules in their atmospheres. And there's just a very, very broad space of discovery here. Let's put this in a more scientific context. This is a figure of all of these 6,000 exoplanets arranged by mass, the Earth masses on the y-axis, as a function of their orbital period, so how long it takes these planets to go around their respective stars. And I've put the solar system planets on here, so I, Europa, Earth, Venus, Mars, here are the giants. And you might notice right away that where we see the exoplanets on this graph is not where we see the solar system. This is not because we think that exoplanets don't form in this area of parameter space. This is an observational bias. It is much easier to detect massive, big, and even hot things close to their stars than it is to detect small, less massive things very far from their stars. As we improve our detection techniques, we may be able to push our discovery into this part of the space. So we detected all these planets. We like to categorize things in astronomy. So here's some big categories. A Jupiter mass planet very close to its star is a hot Jupiter. A Jupiter planet a little further away, that's a more cool Jupiter. And then down here, we have this map of subdimensions, water whales, rock planets, everything small. And I've highlighted rocky planets here because that's what I'm going to talk about. I hope that's why you're here today. So let's do a little history. The first exoplanet was detected in 1995. They trickled in rather slowly for a number of years. And then, as you can see, there were a couple of big jumps here. Those big jumps came from the purple discovery method, that's the transit discovery method. And they all came, or most of them came, from the Kepler space mission. This was a telescope that launched in 2009. It was supposed to last till 2018, but its reaction wheels failed in 2013. So we had 4 years of Kepler. Kepler stared at a single patch of sky for 4 years. This is the Kepler field of view, just above the Milky Way midpoint in the Cygnus constellation. That's the Swan. And Kepler detected planets via the transit method. So as a planet orbits its star, you may get a lucky alignment such that as the planet passes in front of the star from Kepler's perspective, you see that dip. And if you keep watching, especially for 4 years, and you see that dip again and again and again, that is telling you that there's probably a planet there. So even though Kepler only really lasted in its prime mission for 4 years, it actually detected over 3,000 exoplanets. More than half of the planets we have today are from Kepler. It was not bad for a mission that ceased its prime operations over a decade ago. Because Kepler detected all of these planets in the same way, with the same method, looking at the same patch of sky, you can actually do real statistics with these detections. And we can learn something. Exoplanets can teach us something that we don't know just by looking in the solar system. So Kepler, of course, we never do anything on our own. We always have our colleagues and collaborators. Kepler got help from Gaia and ESA missions to detect distances of planets, and to Keck telescopes to tell color of the host stars. Many other observatories went into this as well, but these are some big ones. And on this histogram, we have the number of planets per star with orbital periods less than 100 days, as a function of the planet's size and Earth radii. And what you can see here is that there are not many big planets compared to the small ones. It turns out small planets are the most common planets, at least in our local galaxy. Not only that, these planets, with about 2.5 times the radius of the Earth, are the most common. We don't have a planet like that in the solar system. So Kepler really taught us something here that we would not have known if we just looked within our own backyard. And that's really the promise and the power of exoplanets. So we do have rocky planets in our solar system, and this is their family portrait. Mercury, Venus, Earth, and Mars. What I find amazing is that even with just 4 rocky planets, there's an incredible diversity of atmospheres. We have Mercury, basically a bare rock. We have Mars, a very tenuous atmosphere. It's difficult to land on, but also you can't breathe it. And then you have Earth and Venus. Earth and Venus are fascinating. They're almost the exact same size. But we know they're very different. We're very happy here on Earth with our oxygen, with our 1 bar surface pressure. If you were to go to Venus, you would be walking around with 100 times the weight of Earth's atmosphere on your shoulders. The air is full of sulfur dioxide, with acid rain, not good. But these planets, if they were orbiting some other star, would be very, very similar to us. And the real difference that we might be able to access is in their atmospheres. We want to detect the atmospheres of exoplanets. This is our Earth's atmosphere, protecting us from the horrors of space. It is very thin. It is very small. It's very difficult to detect. So how are we going to do it? First, you need a sample. Kepler found a lot of planets. We want to look at planets really up close if you want to see their atmospheres. You need the nearby rocky exoplanets. And Kepler while it gave us the power, statistics did not give us planets that we could really study. So here's Kepler again, looking at the Cygnus constellation. And if you projected Kepler's gaze onto the galaxy, it's staring at one patch of sky, it's going really deep. It's detecting lots of planets far away. We want the nearby ones. So in 2018, we launched the Transiting Exoplanet Survey Satellite, TESS. TESS has the opposite mission. It is tiling the sky every month or so, and it is looking for the brightest, closest thing. As you can see the difference in extent, but of course we're getting way, way more coverage. This is great. We also have to keep in mind the point planets orbit stars. And so you really need to care about what stars you're looking at. Now, we call this the M-dwarf opportunity. An M-dwarf is a type of star is much smaller and cooler than the sun. This is an M-dwarf, this is a sun-like star or a G-dwarf. If you're looking for a small rocky planet, the same size planet around an M-dwarf versus a sun-like star, you're going to get a much bigger transit signal around an M-dwarf than around the sun. So it's just a ratio of areas. Another bonus of M-dwarfs, there's a lot of them. 75% of our neighbors, our stellar neighbors, are M-dwarfs. Not so many G-dwarfs. Okay, that's great. There's something even better about M-dwarfs. Which is because they're cooler, their planets orbit closer to them. So this is the solar system down here. We're going to be in the mark. And this, if you zoom in really, really close and magnify that by 25 times, this is an M-dwarf system. This is a real system. It's an artist's impression of a real system, the TRAPPIST-1 system. And this system actually has 7 rocky exoplanets orbiting it. Some are in this sort of green area, which is denoting the quote-unquote habitable zone. This is great, because if you want to detect and characterize a planet, you want to be able to look at them over and over and over again. So we're going to skip that a little bit. This is an artist's impression of the TRAPPIST system with the planets orbiting around. And this is an artist's impression, but this down here is real data that we have detected from the TRAPPIST system. And you can see these are all transits going around and around again and again. You can see this sped up time here. But within a few days, you're getting many, many transits over and over. This is allowing us to detect them easily and try to characterize their atmospheres, if they have. But there's one problem with M-dwarfs. They're not so nice for living around. This is a salami, but it's telling us something important. It's illustrating that M-dwarfs are very active at high energy. They flare, they have these things called coronal mass ejections. If you are a little planet trying to hold on to a little atmosphere around an M-dwarf, this might not be good news for you. And the real question is if rocky planets that are orbiting these M-dwarfs, our best chance right now for detecting and characterizing them, do they even have atmospheres at all? This comes to this concept of the cosmic shoreline. It's a fancy name for a very simple concept. So we're now moving again to the graph. We have the total amount of high energy radiation that a planet might receive as a function of the planet's gravity. So more gravity, hold onto an atmosphere more tightly. So let's bring Venus here. Good amount of gravity, not so much high energy radiation. They're happily able to hold on to their atmospheres. Have one here. Mercury, not much gravity, too much high energy radiation. It's a bare rock. Mars stands right on that curve, just a little atmosphere, but not a big one. So this cosmic shoreline, this dividing line between the have atmospheres and the have not atmospheres, holds for the solar system. This line is drawn actually from the solar system. It's a sort of empirical line. We just see it in the data. We don't ask too many questions. Now, you can plot all these rocky planets onto these exoplanets. But those exoplanets are not orbiting the sun, they're orbiting M-dwarfs. And we don't know if this idea, this cosmic shoreline, dividing what has an atmosphere and what doesn't, holds elsewhere in our galaxy. So we've got a look. So the mission, you choose to accept it, which is to study the atmospheres of rocky exoplanets. And dwarf rocky exoplanets, right? These are the ones you can see and the ones you can study. Okay. There's a few ways that you can study a transit exoplanet. So we are assuming that these planets are tidally off. Just like the moon is tidally off to Earth, the moon always keeps the same face, its same face looking at the Earth. We assume that these planets, because they're so close to their orbit, stars, have a permanent day side and a permanent night side. As they go around, you can look for the transit. This is a good detection method. There's a big signal. But if you're looking for an atmosphere, that is probably stellar contamination because of these very spotted surfaces these dwarfs have. It can contaminate your signal. You have an eclipse. This is when the planet goes behind the host star. Not as much as really no stellar contamination because the star itself is not changing while the planet is going behind it. But it's a very small signal. And then, of course, we do a phaser. This has the maximum amount of information. You get the transit, you get the eclipse, you get everything in between. Then it's expensive. It takes a lot of time. And we try to be very responsible with our telescope time, especially the James Webb Space Telescope, because we want to get the maximum amount of science. I'm going to focus on this secondary eclipse method. This is what I use mostly in my research right now. And the point is that we're actually looking for this thermal emission from the day side of the planet. This is how this is working. So when the planet is about to pass behind its host star, you're actually detecting light from the star plus planet system. So there's flux coming from the star and also from the planet. When the planet goes behind the star, hiding behind the star, you can tell how much of that light is coming from the planet's surface. If that planet has no atmosphere and it's very, very hot, a lot of light is coming from that planet's surface, and you will measure deep secondary eclipse depth, which is what we're seeing here. Deep secondary eclipse depth, and this will indicate to you that this is a hot barrier. However, if there is an atmosphere on this planet, atmospheres are like fluids, they can take in energy and move it around the planet, effectively cooling that data, and you will see a shallower eclipse, perhaps indicating to you that there is an atmosphere. So this is the method we're going to use, and the key that James Webb gives us access to is this infrared. If you're looking for thermal emission, thermal energy heat, you need to go into the infrared. And that's what JWST has given us access to that we didn't have to. Okay, here's our cosmic shoreline. We have our methods, we have our infrared capabilities from JWST. So let's take a look at some things. This is a survey that I did. That is not the only one. This one I'm going to talk about. And this was to look at 9 rocky exoplanets transiting, eclipsing their dwarf stars. We're going to try to see if they have some atmosphere. So let's look at some data. The first data from this survey actually came in a couple of years ago now. This is when JWST pointed at the first planet in the hot rock survey. And this is the first image that was taken of that system. This is what the raw image taken with JWST looks like. And it has this funny shape because JWST has this hexagonal segmented mirror. Now remember, we are not resolving the star. I know it looks kind of like a star, but all of those pixels, all of that light is scrambled up. We don't know which light is coming from the star or the planet. This is just how telescopes spread light onto their detectors made of pixels. So maybe impressive funny, I don't know how many of these can come to that are people with galaxies or extragalactic science. Exoplanet science happens in our backyard. So this star and the planet that is around it is about 60 light years away. A little bit of math will tell you that the light that we're seeing here in this image left the star and the surface of that planet on June 6, 1964. That's not that long ago. If you do a quick Google search, it will tell you that on June 6, 1964 was the first day that the Rolling Stones played on TV in the United States. So that was a great day for the US, and so 60 years later, anyone who's on this planet listening, maybe because I'll This is what the data looks like. This is what the process data looks like. This is done by Bush, who is a graduate student at the Technical University of Denver. This one of these images turns into one data point update. So we stare, we get a lot of data points. And this is that eclipse shape that we were introduced to a few slides ago. This was an exciting first piece of data to get, actually, because the eclipse is a little bit shallow, perhaps hinting at an atmosphere. But this is not statistically significant. We need more data. Add another schedule, and this one shows a very strange behavior, which kind of has indicated this is pink signing space. What is this? We don't think it's from the planet, not alien. We think it is probably, it is most likely systematics from the instrument, from the telescope, and perhaps a flare from the star itself. Whatever it is not secondary eclipse. We cannot combine, this is not giving us any more information about what's happening here, and so we're kind of stuck with this not statistically significant data. That's okay. Could apply for more time with the contingency, and she got it, bringing in more observations, and those are happening next year, so stay tuned. But there's no real result here, it's just this is what most of our data looks like. This is a much more typical planet. This was analyzed by Natalie Allen, a grad student at Johns Hopkins University. These are two observations. They were sat really nicely together. Here's the cleaned up secondary eclipse data. And the result is that both agree with the kind of bare rock case. And indeed, this has been the much more common finding, that most of hot rocky worlds orbiting dwarfs are airless. These are the 9 planets in the hot rock survey. There's that maybe question mark one. Basically, all of them are bare rocks. And we're not the only one. Other people have checked. These are actually all of the bare rocks we have detected. Don't be disappointed. You might also wonder, well, isn't this maybe what you expected? If the solar system cosmic shoreline holds for dwarfs or other stars in our galaxy, maybe we would expect this. Why don't we go over here? These are the toughest cases. They're the coolest planets because they're not so hot. They may have atmospheres. They take a lot of time. And luckily, we actually have a plan to move onto this side of the so-called cosmic shoreline. And this is called the Rocky World Survey. I am not the lead of it. I helped to implement it. This was a designated by the director of Space Telescope Science Institute. So she designated a bunch of time on PwC to continue this project to go after the hardest planet. This happens for exciting fields every few years or so. So we're very fortunate in exoplanets to catch the director. The data from that is going to start here as well. Okay, good question, right? Are we going to learn? Yeah. I don't know. But this is what I think about when I think about this question. So remember where we're looking in our galaxy for planets in the Milky Way. Here was Kepler. Remember, Kepler stared at that 1.5 sky for 4 years. It got very deep in this one direction. We have TESS, the Terrestrial Exoplanet Survey Satellite that's studying our nearest, brightest exoplanet neighbor, right over here. And then you have what's coming up next, which is the Nancy Grace Roman Space Telescope. Like Kepler, it's going to stare in the direction that's looking right into the heart of the galaxy. I'm going to talk a little bit more about Roman instead. But you can see by eye, we're not covering a lot of ground. We are looking very locally. We don't know what exoplanet population in this part of the galaxy looks like. We can guess, but we don't know. But here's what we will know, and I want to touch base on Roman again. So this is, remember, the 6,000 exoplanets we have now. Nancy Grace Roman is supposed to launch next year, and will detect 15 times more, about 100,000 more detections. And it will detect them via the transit method over here. It also uses a method called microlensing, which will get us to these lower mass planets orbiting farther from their star. These will be too far away to study, but we will actually know for the first time what the exoplanet demographics look like overlapping the Earth rocky, the solar system rocky planets. So think about this when you're wondering if there's life out there. It really could be possible, and it could be possible we are not able to see it yet. All right, to really get to the next level, it's going to take another big leap forward in telescope instrumentation. This is one idea. There are many floating around. This is an idea to look at Earth-like planets, not around dwarfs, but truly around sun-like stars. So Earth-like orbits around stars that are the mass, the radius of our sun. And to do that, the transit method is going to get you. You want to wait 365 days for Earth to transit the sun. You want to directly image it, which means you have to somehow block out all of the light from the star in order to reveal the few photons coming from the planet. This is a many decades long, it was 2 decades long process to try to develop this instrumentation to be what may become the habitable world system. But for now, we are 4 years into JWST, almost 5 years now. A lot of discovery is still to come, and I hope you all continue on this journey. Thank you.
Good, Hannah. Great talk. We will open the floor for questions. We're actually going to board you with how much run to the follow-up and talking to the
Question. Anyone has questions?
So I have a question about the transit method of looking for the planet. So does it like so that method usually only work for planets that are very close to the sun, which means the rocky planet, and also they have to be on the same length as the star, right? So like their orbit plane should be on the same length as the star. That's the only way for that to work, right? It's working on the way.
Yeah, the transit method relies on the fact that you get a higher probability of a transit the closer the planet orbits to the star. And yeah, you have to have that lucky alignment. Yeah. So not every planet.
Also, can you explain how the method you are using right now to detect the advantage? The secondary methods.
Yeah. So with that visual aids. Yeah. So the secondary eclipse method, when you know the planet is there, we detected it via transit. That's the bigger city of how you detect. The planet transit, there's a pretty good chance it also passes behind the star, right? Because these are pretty flat orbital planes. When it goes behind the star, if there was a tiny bit of light actually coming from the surface of this planet, from this hot surface, these are photons in the infrared emanating from the surface of this planet. But of course, we don't see it. It gets separated from the star. We just see this one big stream of photons. But if we watch in time, as the planet goes behind the star, we will miss its light. It will be hiding from us. And then this proportion came just from the planet. Yeah.
Okay, thank you.
Time is an important factor.
Thank you. I understand that when they did the test, it was cooler than they expected. And they thought that might indicate atmosphere. But how did you know what the expected temperature was to begin with?
That's a good question. Yes, so it's something you can calculate analytically, based on the temperature of the effective temperature of the star, the distance of the planet to the star, and the radius of the planet to give you kind of a cross section and how much light is intercepted. Most of that information we can get, most of the information about the planet we can get from watching the transit happen over and over. If you solve, there's an analytical shape that transit has. You can solve for that. You can have numbers. There's ways for studying stars themselves, which can help you get to the temperature of the star. So you can make this kind of maximum temperature calculation. It's a good question because sometimes there's uncertainty in it. So that's something we have to be very careful about. And there's like efforts now to better characterize these M-dwarf stars. They're difficult for many reasons. They're difficult to characterize. So if you're off in that temperature, it can be it can affect your results. So it's about a very careful analysis there. Maybe I didn't go too deeply actually. Thank you.
Hi, thanks for the talk. I'm just curious to know what's the most interesting thing of your research and just curious about that.
What's most interesting, like that I've learned?
Yes. Yeah.
Oh. Well, everything. Actually, since we just talked about, I think I started in this field of exoplanets because I wanted to study exoplanets. But it turns out I mostly study stars because planets orbit stars. And you sort of, you think like, oh, I'll be detecting volcanoes or exovolcanoes. No, most of the time I'm thinking about like, well, it's an M-dwarf, has this kind of spotted surface and flares like this. Is this affecting my data? Is that what I'm seeing? And instead of being mad about it, I think it's really good. And actually, a whole part of my research were actually studying M-dwarfs and the UV. Because it's actually really interesting to learn about. They're not a well-studied star of a group.
So when you're looking at the planets, you're looking at the fundamental makeup of it, specifically when you look at the stars. I know you can kind of see like what I'm saying. I'm vaguely remembering that it looked like the helium and hydrogen, like some of the type of stars. Are there kind of looking at the elements makeup of the planet that you're studying, or is that something we can't see right now?
No, that's So we can't see it for these, but I'm just talking about these little rocky planets because I think they're cool. We actually know about we know about a ton of these types of planets. For these bigger ones, for sure, and even some of the bigger ones here, it's very hard to get to like the radius we detect, but then the low mass. So if you have a low density, well, you can't be all rock. And so we know that there must be an atmosphere there. And actually, for these bigger planets, we have detected carbon dioxide and water and methane. Certainly for the big ones, there's been a huge amount of research trying to understand, can we tie that back to where, how did you get into Jupiter here? Did it form here? Probably not. That's probably formed out here. We have a lot more material in migrating sands. There's a lot of work looking at the molecules of those planets.
What's the evolution of the planets is like from how it was before and change from its star now?
That's more with the theoretical pursuit, right? Because it's not changing appreciably in a human lifetime. But you try to look at the stages, maybe.
This will be our second last question.
So I figured I'm curious if you can go back to slide 33, the question about one of the assumptions you stated there. I just wanted to know. Of course. Okay. Actually, this, yeah, perfect, okay. Exactly, so you mentioned, there is an assumption that there's a, like, essentially the planet itself, stays sort of like static. Is that like different from your gravity faces one way?
Yes.
So, I mean, correct me if I'm wrong, my understanding is, how it tilts on Earth, right? And this has been that, insane to see in other planets as well, right? So over the years, eventually, I don't know if that's a fair question to ask. Just want to like ask, is that something that you sort of like having your research or how do you sort of like talk about that?
We can we can't detect precession on exoplanets with a pretty slow process. We can detect that slight difference of alignment for big planets. You can't really do that for these. What we assume for these planets is that because they are so close to their much more massive, much more stars with a much bigger gravitational well, that they become highly locked and synchronously rotating, and that they have their axis of their orbit pointing the same way as the axis of their star's rotation. But ours is a little bit off, we have different configurations in the solar system, but for these planets that are so close to their co-stars, the tidal forces are just so strong that we think that is not happening. At least not on a time scale that would sort of matter for these observations, right? Maybe there is a slow migration where a planet can kind of wiggle around and sort of eventually turn. That might be happening on sort of much longer 100,000 million year time scales. But effectively for our measurements happening over several years, even decades, the planet is not changing that much. Yeah.
Hello. Regarding the fact that most of the planets that we are discovering are either gas giants or Jupiters, or either if it's rocky planets, they are not located in the Goldilocks zone where the water can be in a little bit more. And even this planet that is what the great dwarf is unlike what most of the people think is not very fine tuned for life. And around 99% of the species that have lived on this planet is already extinct. What are your thoughts that we have the only planet on the cosmos that literally harbors life?
Cosmos?
Yes, the universe. We are the only one.
Oh, that would be like statistically improbable, right? Because there's 100 billion stars in our galaxies, and there's, I don't know how many galaxies, there are a lot more than that. So, I mean, on some galaxy somewhere, why not? But we are not accessing that information anytime soon. Maybe yet.
Never.
Right. So the question, I think, that is, if you're going to ask about life, it has to be, is it close enough and occurring close enough in time we would actually detect it? And I don't know. We haven't looked very much. Yeah.
Thank you for the fantastic questions, and one more round of applause for